G'day viewers. In this episode we establish 5 significant outcomes. Number 1, very importantly, we accomplish a key research objective which Tshipa was unable to achieve, that is, relating spin angular momentum to particle radii. Number 2, we show that spin angular momentum derived particle radius decreases as mass moment of inertia increases. Number 3, our spin angular momentum particle radii derivation does not contain any electric or magnetic information, hence it cannot be interpreted as being related to any electromagnetically associated radii values. Number 4, the proton may be modelled as a rotating disk, yielding a particle radius to within 0.08% of the authoritative, experimentally verified benchmark presented. Number 5, the neutron may be modelled as a rotating hollow sphere, yielding a particle radius to within 0.008% of the authoritative, experimentally verified benchmark presented. Okay, let's get into it. Let's begin our journey by identifying where the Tshipa research article can be found, as we did in episode 98. Now that you know where to find the primary artifacts, let's fix Tshipa's spin angular momentum problem, which we identified in the previous episode. If you have not already watched episode 98, please pause this presentation and watch the previous episode before proceeding. Well, assuming that you have followed my instructions, let's move on. The particle radii derivation process is remarkably simple by leveraging off episode 98. Once again, we urge all viewers to review episode 98 prior to proceeding. Okay, let's walk through the process in a stepwise manner. Step 1. Formulate an expression for the total energy of the rotating energy ring as depicted in episode 98. Step 2. Assume that the total energy of x sub n particles equals the propagation energy of x sub gamma photons. Step 3. Execute the following substitutions. Assume all physical measurements occur in a co-moving lineal frame of reference. Step 4. Assume x sub n equals x sub gamma and solve for r. Step 5. Utilizing the spin angular momentum equation, execute the following substitutions into step 4 with respect to baryons. Please note that beta and lambda sub beta have vanished from the solution. Step 6. The radii for all baryons is given by the absolute value of the equation defined in step 5. Step 7. From episode 98, we know that all meson and boson radii must be given by the relationship shown. Step 8. Evaluate particle radii solutions utilizing common mass moments of inertia configuration coefficients. Example mass moments of inertia appear below. Please note that hoops may be considered to be massive strings. Let's now look at some spin angular momentum generated particle radii results. Our spin angular momentum generated particle radii results, based upon Tshipa's original particle listing, exhibit the following characteristics. Number 1. Radius decreases as mass moment of inertia increases. Number 2. They do not contain any electric or magnetic information, hence they cannot be interpreted as being related to any electromagnetically associated radii values. Okay, so how do we interpret the physical meaning of these spin angular momentum generated particle radii? To answer this question, we shall utilize established experimental benchmarks to act as frames of reference. It may seem astonishing to many viewers, but there are only 2 particles which have had their physical dimensions measured to high precision, that is, the proton and neutron. Even then, of these 2 particles, neutron size measurements are not as straightforward or precise as the proton. We shall utilize the experimentally verified exact analytical solutions published by Storti in 2007, then again in 2009 by Storti and Desiato as our benchmarks. Moreover, we recommend all viewers to watch episode 5 on this channel for a video presentation pertaining to the formal derivation of the zero-point field equilibrium radii appearing on screen. It should be noted that the zero-point field equilibrium radii we derive coincide with the proton root mean square charge radius and the neutron mean square charge radius. This means that the zero-point field equilibrium radii equations appearing on screen may be considered to be authoritative and definitive. At the bottom of the screen, we compare our spin angular momentum solution to the benchmark zero-point field equilibrium radii solutions appearing mid-screen. Our results show that the dissimilarity between Table 2 and the experimentally verified benchmarks are minimized as indicated by the purple emphasis. In the case of the proton, the best fit occurs when I sub x equals a half, such that the deviation from the experimentally verified benchmark is less than 0.08%. In the case of the neutron, the best fit occurs when I sub x equals 2/3, such that the deviation from the experimentally verified benchmark is less than 0.008%. Okay, let's now summarise what we have learned. On our journey, we have learned 5 significant lessons. Number 1, we have accomplished a key Tshipa research objective, that is, relating spin angular momentum to particle radii. Number 2, particle radius decreases as mass moment of inertia increases. Number 3, our spin angular momentum particle radii derivation does not contain any electric or magnetic information, hence it cannot be interpreted as being related to any electromagnetically associated radii values. Number 4, the proton may be modelled as a rotating disk, yielding a particle radius to within 0.08% of the experimentally verified benchmark. Number 5, the neutron may be modelled as a rotating hollow sphere, yielding a particle radius to within 0.008% of the experimentally verified benchmark.